Hello and welcome to lecture 6, which is called Extensions of Graph Theory. And it also could be called, in addition, extensions to network theory. Network theory is what complex systems scientists usually call the statistical variant of graph theory, where you look at very large graphs. And so you should read this lecture 6 as both an extension to classical mathematical graph theory, but also as an extension to network theory, which is applied to complex systems. So we go into a short overview of the lecture today. So the problem with graph theory is that you have two defects, and these defects are with respect to mathematical modeling. Of course, there is nothing wrong with graph theory as such. It can solve solve many applied problems, so it's very valuable. I don't want to diminish that in any sense. But with respect to mathematical modeling of complex systems, graph theory is not the end of all wisdom, and the same holds also for network theory as it is emphasized inside the complex systems community. So what are the defects with respect to mathematical modeling? There is the problem that graphs and networks are based on binary relationships. So if you have a system where the system components interact with each other, for example, then you describe in the graph only mutual relationships between any two objects, but never something like a real group structure where things would be grouped together. So that is really a problem, and that is defect number 1. And defect number 2 is nearly all scientific empirical systems actually have a multi-scale structure. And this is immensely important. There is a lot of mathematical theory describing multi-scale structure, but the skeleton, the structural description of that is not very specified and not very well defined, and this is exactly what I want to do in this lecture. So we have to introduce a structural concept, a graph kind of concept, which describes a multi-scale nature of a certain empirical system. So that will be defect 2, which we will address in this lecture today. Okay, so this is a good preparation for what comes next. And the next question we are asking is, what is a bipartite graph and why is it important in this lecture? Well, first let's just go through the definition. A set theoretic structure consisting of 3 sets V1, V2, called the first and second set of vertices respectively, and in addition a set E called a set of edges is a bipartite graph. G, which is expressed as G of V1, V2 and E, if the set of edges E is based on binary relation. So it can be written as a 2-tuple V1, V2 between elements of V1 and V2. But here you need that either V1 is in V1 and V2 is in V2, or V1 is in V2 and V2 is in V1. So there are no, and that is really important for the definition, there is no binary relation inside the sets V1 and V2. So this is completely separating the two sets V1 and V2, and that is exactly why we have this notation as you can see here. So G of V1, V2 and E. Right, so you have here a figure, an illustration, which shows you a typical bipartite graph. So here you have one of the sets with all the vertices of the set V1. In this case, we have here 15 vertices in V1. And then you have here vertices in the set V2, and they are denoted from L1, L2 up to L5. Now let's just think a little bit about what would be a typical example, a real-world example that could be described by this bipartite graph. So bipartite graphs are often used, for example, in so-called matching problems. So there are two groups of people and then you try to match them. This would be one interpretation. So here, for example, every member of V2 here would be matched to several members of the group here in V1. But you have also another interpretation, and that will be relevant in a moment, and that is you have, instead of a matching problem, you have here a group structure described by the bipartite graph. So you can also imagine that L1 describes a group, and then this relationship here, of each of these edges which are emanating from L1 would indicate a group membership. So every vertex here is in the group L1. So this one, V2, is also in L1, V3 as well in L1, and so on and so on. This is very important for us in the lecture, because what you see is, instead of having the relationship, the binary relationship that, for example, V1 is related to V1, and this is expressed by this edge. Instead of that, we have another interpretation, and that is this element V1 of the set capital V1 is actually an element of a set represented by a vertex in V2. So L1 is an element of V2, but it is also at the same time a set. And then these edges are not describing binary relationships, but they are describing a set theoretic relationship which is being an element of. So we discuss in this lecture, and that is extremely important, two types of edge formation. One is by the binary relation, and of course then the binary relationship could either be described by a normal edge or an arrow, depending on whether the binary relationship is ordered or unordered. And we have a second relationship that we use with edge drawing, and that is the set theoretic operation being an element of. So please keep that in mind. Let's go further. Now we discuss what is a hypergraph. And yeah, a hypergraph is a set theoretic structure now consisting of two sets, V called the set of vertices and L called the set of hyperlinks. And this is a hypergraph which we denote by capital H, and H depends on the set V and on the set of hyperlinks L. If L is a family of sets L such that each L in capital L satisfies that L is a subset of V. So in other words, we are now forming here subsets of the basic set V, the set of vertices. And each L in this set capital L, the set of hyperlinks, is itself called a hyperlink. Yes, so you see already with the two notations that bipartite graphs and hypergraphs somehow seem to have something to do with each other, and I would like to explain that. So first let's go to a hypergraph example. Yeah, so instead of drawing binary relationship between the like this one or this one would be another one, or this one would be another edge I could draw in the original set of vertices, which are still the set V1 up to V15. Instead of that, I draw now Venn diagrams. So the Venn diagrams, so for example this one, is indicating that now you have an n relationship between different elements, and so this one would be indeed a relationship between all the elements V1, V2, V3 and V5. And this relationship we call L1, and this will then be interpreted as a hyperlink according to the definition we just had discussed before. And in this example, so you have 1, 2, 3, 4, 5, 6 hyperlinks. Sorry, five hyperlinks, as it is written here. Okay, let's go further. So what I want you to see now is that actually the two things, the two concepts of hypergraph and of bipartite graph can be easily matched with each other. So the two things actually have the same information, or in mathematical terms they are equivalent as structural descriptions of relationships between elements of a set. So how does that work? Well, consider first the hypergraph H, capital H, and then consider a bipartite graph G with all sets to be specified. So first we choose V to be equal to V1. So we identify V1 with V. And now we choose that V2 should become L. And the set E will be dealt with in a separate way. So what we do is, after this first two equivalences, so between V and V1 and L and V2, we construct now the set E of the bipartite graph G of V and VA, such that we have that each E is a binary relationship between sets of V and the set of hyperlinks L. And this is even only if actually V is now an element of L. So in the construction of the hyperlink we have that we use this element of notation because you can actually now be an element of a hyperlink if you interpret that in the hypergraph kind of way, because the hyperlinks are actually nothing else but subsets of the set V. So making these choices, we have shown that every hypergraph H can be transformed into a bipartite graph G, and vice versa. If we like to construct E as unordered, then we require that with E equals the two tuple VL in E, also E prime is in E. So this is actually a remark for later. You know, when you have this kind of set theoretic construction where V is an element of something, So V is an element of a particular hyperlink L, small l, then it doesn't actually matter whether you draw this as an edge or as an arrow, because you could of course interpret that, yeah, you have two sets, and if one is the set of basic objects, then you just draw a normal edge, not an arrow, if this is an element of an hyperlink. But you can also interpret this being an element of as a directed binary relationship, so you draw it as an edge, as an arrow, excuse me. But in this lecture we will stick to the convention that if we have the set theoretic setting that V is an element of a hyperlink small l, which itself then forms the set of all hyperlinks capital L, then we always draw an edge and not an arrow, because this is sufficient, gives us sufficient information. Right, so we have discussed how we can convert n relations, which you would construct in a hypergraph, as hyperlinks. How this can be converted back into graph theory by showing there is an equivalence to a bipartite graph. A bipartite graph, of course, is completely an object of graph theory. So we see that in the end we are not restricted too much, so we can still recover all results from graph theory if we are actually introducing hypergraphs and n relations. There is another way to go from ordinary graphs to n relations, and that is you can also go to simplicial complexes directly, and I want to explain what is really the difference for a moment. So you typically base the simplicial complexes on this notation of n relations. So an n relation can be written like that, as a mapping of the basic set V to the power Q, and then you have a mapping to 0, 1. This is just saying either this relationship exists or does not exist. So if rho would map into 0, then there would be no such relationship. If it would map to 1, then there would be such a relationship. So this is a kind of Boolean approach. So the elements of V to the power Q will be these Q tuples, which you have defined here. Now the question is, of course, how do you define whether this Q tuple is actually ordered or unordered? We had already discussed this with respect to two tuples and graph theory. So, of course, this works by having permutations, and we will discuss that on the next slide. But the point about simplicial complexes is that they also describe these n relations that are given by rho, but in the definition you always say that every subtuple, so having only a certain length less than Q, is actually also a part of the relationship. So this would mean, if we go now back to the hypergraph example, that would mean is if we want to construct out of this hypergraph example actually a simplicial complex, then we would also need all two relations, for example. So we would need also this hyperlink, we would need this hyperlink, we would need this hyperlink, and then we also would include all three relations. So we would also have to include this hyperlink, and then we have to include this hyperlink, we have to include this hyperlink and all other combinations of 3. So this means there is a kind of relational closedness with respect to simplicial complexes. Very often in application that is absolutely fine. We can discuss that later. Sometimes this is a little bit artificial and not really necessary. And so the question is why you would like to use simplicial complexes instead of hypergraphs. But on the other hand, there is a very good argument for using simplicial complexes, and this is and here's an example of a simplicial complex, and this is because then you can use all the established theory of that is related to simplicial complexes, like cohomology theory, for example. So, and that is used nowadays very often in data analysis, in so-called topological data analysis. So there is sometimes a reason why you include in something all sub-relationships. So this, for example, this triangle here is describing a 3 relationship, and you see that also all 2 relationships here in this simplicial complex are actually realized. So yeah, that is the simplicial complex. So you can also define whether a simplicial complex is having an order or not an order. And as I said before, this is exactly given by permutations of the n relationships between the q relationships between q many elements of the set V. Okay, now let's go back to mathematical modeling for a moment. So we have introduced now the concepts of a hypergraph. We have included the concept of a bipartite graph. We have already discussed before directed and undirected binary graphs, so graphs that are based on binary relationships. And now we also have introduced simplicial complexes. So how is that related to mathematical modeling? Well, I discussed that in a previous lecture, but let's repeat it quickly here so that we are up to date. What we have is a set of basic objects, which are always denoted by calligraphic O. And then we can introduce the type graph, which is representing every type of, so the type is a classification of the basic objects in the set O. And so you see this vertex here, for example, is representing all basic objects that are of type T1. So that means we have exactly this set theoretic relationship, so being an element of. So all basic objects that are of type T1 form the group that is represented exactly by this type T1. So you see there is a pattern emerging how actually the type graph was put on top of the basic objects as a hypergraph, and the vertices of the type graph now can be interpreted as hyperlinks. So, for example, we had this hierarchical classification of a human population. So you have here on the lowest level, you have here all the individuals of a human population. Then you can characterize the human population by age classes, and you can see that different individuals here from the basic set, they form different age classes. And then you could also classify at the same time all the individuals here on the human individuals here by having their main locations at different places. So for example, these are the ones that are working at schools or educated at schools, and then these are all people that are shopping in a supermarket or working in a supermarket, things like that. And then on top you have the disease states, so every individual so this individual, for example, can be in the recovered state, so you introduce here a simple SIR model as a classification. So S is the class of susceptibles, I is the class of or type of infected people, and R is the type of recovered people. So you see, you can now draw a classification. So this individual, for example, would be an element of the set of susceptible people. So what is interesting here is that I did draw this classification here in a hierarchical way, but actually because every individual here has a link to each of these types, so here to the disease states, or here to a location, or here to an age class. This means that all the classifications are actually independent of each other, and each one of them, so age classes, locations, and disease state, are all direct classifications of the basic set, which here consists of human individuals. So this means this is not a real hierarchy which you are drawing. It's 3 different classifications on top of each other, but they are independent of each other. So you could actually draw this classification, and this classification parallel to each other. And that wouldn't take away any information on the system. So you would, you would have a basic set, and you would have 3 different classifications on top of it. But of course, this is not always how you do classify. Here the classification actually would consist of 3 bipartite graphs, which then can be reinterpreted as 3 different hypergraphs, which then make the classification scheme. But let's go to another example where this is not the case, where you have a real hierarchy in the sense of doing group formations, group of group formations, group of group formations, etc. So how is that working? Let's go to chemistry now for a little while. And we introduce a very simple hierarchy in the space of molecules, and that is we just count how many atoms are in each molecule. So you have here then as the first classification, then you have the periodic table of atoms. Note that this is already a classification. It's not the set of basic objects. So the basic objects here would be actually below the first classification, and that would be the set of all atoms in the universe, whatever they are, independent on whether they are hydrogen or oxygen or carbon. It wouldn't matter. So the basic object set here would be below and would be consisting of all atoms of the universe. And then the first classification would be the classical periodic table of chemistry. In itself, I should mention that I think one of the major scientific achievements of humankind. And the periodic table then can be used to build up higher order molecules, as I would call them in this context. So you can build up first with relatively simple molecules that have only 2 atoms. That would be our first level of the hierarchy. And then you can build up 3 atom molecules, 4 atom molecules, and of course you have here many more levels which I haven't drawn in this picture to keep it simple. So what do I want to achieve with that? Well, I want to show you with that example that here you have a true hierarchy in the sense that you have group formations. So each molecule will now be interpreted as a group of atoms. So for example here you have a molecule consisting of 2 different atoms. So this one and this one. So I interpret this 2-atom molecule as a group that uses this type of atom and this type of atom. So this could be, for example, carbon, and this could be, let's say, oxygen. So this vertex here on that level would represent carbon monoxide. Yeah, so you should keep in mind now a molecule is a set of molecules, and in the simplest case a set of atoms. So we can work our way up. So for example, this molecule here itself can now be used to compose something that is even higher up, maybe at the 3-atom level. And because that is a 3-atom level, so it would go from the classification of 2-atom molecules on one hand, and it would go all the way down to the classification of atoms which are 1-atom molecules. It's important to note that this is already a set. So this would represent the set of all atoms of the universe in a specific type of atom, like carbon. And then this one would, so this set here, one up, would be exactly the set of atoms, of types of atoms. It would be the set of types of atoms. So this is, this is already a group of groups. You have to realize that. So now we are really constructing a true hierarchy here. So this is a group of groups. And this here, can be already a group. No, this not already, but this here, for example, could be a group of groups. So, it can be composed of 1-atom groups, of 2-atom groups, and of 3-atom groups. So the higher up you go, you have a set of sets, a set of sets, a set of sets of sets of sets, etc., etc. You really should try to understand that what we have done here in this construction is actually a true hierarchical extension of the bipartite graph when we draw it like that. So here you have, so on that level, this together with that level would create you a bipartite graph on the set of atoms and the set of 2-atom molecules. And then we go further up and build another layer, which then is then creating a true so-called multipartite graph. Okay, I think I hope I have explained that nicely. It is a little bit mind-boggling, this set of set construction, I know, but that is really what you do in many scientific problems without often realizing it. So to have a mathematical, rigorous construction of this kind of thinking is extremely important, I would claim. So we go now to the definition of what is a hierarchical hypergraph. Yeah, and I should say in these examples I only have discrete level hypergraphs like in the bipartite graphs. Of course, when we go now through the construction, I have only finitely many levels in my hierarchical hypergraph. Because of this construction of sets of sets of sets, you can realize, because of the problems of set theories, if you form infinite constructions, just think about the Russell paradoxon. That means being finite here in the level set structure is very important, because then you are fine with the cardinalities and consistencies of set theory, whereas if you would allow infinite constructions or even continuum constructions, this would really create a whole mess, as you can imagine, which you could only resolve by going, instead of set theory, going to category theory, which was exactly constructed for such cases. So, so what is a hierarchical hypergraph? So a set theoretic structure, capital H now, is a hypergraph which depends on the basic set V as before in all our set theoretic constructions. And now M different sets of hyperlinks, LM, and you can also write that out. So you can say a hierarchical hypergraph consists of a set V and M many different sets of hyperlinks. But the sets of hyperlinks will be constructed in a very different way now. So you have that L1 is just the usual construction of a hypergraph. So here you have not yet a hierarchy. So L1 is a family of subsets of V. That is exactly how we originally constructed the hypergraph. So you can write L1 as the set of hyperlinks Li1, such that each I is in the index set I. I use here an index set notation just to possibly account for different cardinalities rather than only the natural numbers, but that should not be important here at the moment. And the L1 is such that each hyperlink, is forming a subset, so it's interpreted as a subset of the set V, of the the basic level set which is containing all vertices of this hypergraph, which then will become a hierarchical hypergraph. So you have here, you have a construction by doing subsets of the lowest level set V. And now we work ourselves upwards in the hierarchy. So now we define hyperlinks at level Lk, where k is now going from 2 to m. So m is the maximal number of level where we stop. And now this is a family of hyperlinks Lk as well, so defined as this. But now it is constructed such that any element of this set L, of this hyperlink L, which is an element of the kth hyperlink set, capital Lk. So this is done in such a way that either this 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 set which is formed by small l can either contain elements from the lowest level, so lambda in V, or it can contain elements lambda which are now elements of lower of any lower level than k, so which are elements of L kappa, where kappa is strictly less than k. Yeah, so this is exactly the construction, of having sets of sets, sets of sets of sets, etc. So this kind of construction is now possible with a definition of the hierarchical hypergraph. Okay, so let's go to the interpretation. It's exactly what I said. So the basic set V is equivalent to the set of a basic graph. So we always started in all of our constructions with a basic set of vertices V. And then in the hierarchical interpretation, the elements of V constitute the basic elements of the model, independent on whether this is mathematical or real-world application. Doesn't really matter. So here the higher level sets now, these sets of hyperlinks L1 to Lm, form a hierarchy of groups. So at level L1 they can only form groups of elements of V, but at higher levels they can now form groups of groups, or groups of groups of groups. So for example, L2 can have as elements either elements of V or elements of L1, because both V and L1 are at a lower level of the hierarchy. And L1 itself, of course, are subsets of V. So you have here subsets of subsets. And thus the group membership, if you use now the group membership interpretation, L2 can at most contain a group of groups of members of V. That's exactly what it is. And now you interpret this iteratively, so L3 can at most contain groups of groups of groups of members of V, etc., etc. Yeah, now I show you this very ugly example of nested Venn diagrams, and you can see that if you want to draw a hierarchical hypergraph as nested Venn diagrams, then your drawing abilities soon reach a limit. Yeah, so it's actually good that we have this kind of idea of equivalence to multipartite graphs. So we will make this a little bit more rigorous in a moment. But just look at this figure and now compare this with this figure, because both of them do actually give you exactly the same information. So this here is drawn as a true nested hierarchical hypergraph, which is then a hierarchical hypergraph. So you have to use in the drawing nested Venn diagrams. And here you draw the hierarchical hypergraph as a multipartite graph, giving you exactly the same information. So here you have a nice separation, and we have drawn that before in this way all the time. You have a nice separation into the different levels of the hierarchy. Okay, so we, as I already claimed, so if you have a hierarchical hypergraph, it can of course not be equivalent to a bipartite graph, but here now you have to introduce so-called multipartite graphs. So what is a multipartite graph? A multipartite graph is a set-theoretic structure G, which now has a basic set V. It has now m different level sets Vm, and it has an edge set E. And now you say that you have never any relationships among elements of V and among elements of Vm. So this, this exactly now defines you the multipartite property of the multipartite graph. And as I did prove or construct by construction the equivalence between hierarchical hypergraphs and I showed the equivalence between hypergraphs and bipartite graphs. So now I can do the same kind of construction between hierarchical hypergraphs and multipartite graphs. I leave this to you. You can go through this construction, but it's clear that it actually follows exactly the same way of thinking as for the hypergraph example. But now, of course, you do this iteratively, going from going from level m to level m+1 and so on and so on. Now I would like to introduce level set orders. Why is this necessary? We have seen that sometimes in models, in mathematical modeling, you end up with a situation where the graph is, where the classification is actually just on top of the basic set, but parallel to each other. So I should actually go back to this example of the SIR model which we had. So I should go back to this example for a moment. So realize that now with the knowledge we have about hierarchical hypergraphs, this is of course a hierarchical hypergraph, but actually not a, it's a very degenerate kind of hypergraph, because actually all the links here in this model, so here from here to here, so they go always back to the basic set level O. So there is no group formation in this example. And in our notation, this would mean that this level here, and this level here do actually form only a partial order instead of a strict order. So in a strict order you would have group formations, but in a partial order of the level sets you would only have a classification which always is a classification of the basic set calligraphic O. So let's go back to the precise definition excuse me, of the level set order. Like always with orders, you have these three properties of reflexivity, transitivity, and anti-symmetry that creates you a pre-order. And then you can define level order, so you can compare levels with each other. You can say one level is is smaller or equal than another level L prime, or the other way around. So that is the property of comparability. But of course you can also have a linear level set order with a strict hierarchy, and this is what you need for the definition of a strict hierarchical hypergraph, because there a higher order level would always mean it would only contain elements from lower level sets, but not only from the lowest level. Okay, so I think I did already give you the interpretation. So a partial order of the level set would correspond to a classification in a mathematical model where the classification is in parallel with each other, and then a linear order on the level sets of the hierarchical hypergraph, or equivalently on the multipartite graph, would be that you have a strict group of group formation in these examples. Now I just would like to make the comment that of course you can also weight all these set theoretic structures. It works exactly like in graph theory, so you would have to have one function, the weight function, that is defined on some of the sets that are used to construct this structural model. So here, for example, you have the M-partite graph, multipartite graph. So you would have the ability to weight any of these sets V1 to Vm, but you can also, of course, weight the edges in this case. And R here, as before in the previous lecture, is the so-called record set. If, for example, the weight is just real valued, then R would just be the the real numbers. Okay, so you can weight. Now let's go further. So now we go to combinatorial relational models. So what that is interesting for our discussion now, because many of you might not see the necessity for the hierarchical hypergraph. It's good actually to contrast that with so-called layered graphs. So a layered graph, in my definition, is now a graph which consists of m different graphs. So I discuss here the directed case. So you have m different directed graphs. So each one is using the notation, each one has the set V1 to Vm as the set of vertices. And then you have also m different arrow sets going from A1 up to Am. But now, so these would just be, so far in this definition, this would just constitute m different directed graphs. But now you have, of course, the possibility that you have connections between these different directed graphs. And this is constructed with this set of C of bridging connections. So C is for connections, and C are now binary relationships between vertices of different of these m different graphs. So we will go to multiplexes in a moment, but this is always a good example. So you have, for example, two infrastructure networks, like all the flight connections, and then you have also train connections between different, let's say, villages or towns in this case, and then oh, sorry. Yeah, and then the connections, they would just form the the transitions from one of these networks to the other. So, for example, you step out of the train in the airport and you enter a flight. In this case, you would have a connection between you would have a connection in C between you would have a connection in C between the airport and the train station of the airport. So this would be described by C. An illustration of that is given here. So here you have just these 5 different graphs. They are also drawn as layers, but now these layers are so far completely unconnected. But now you can draw these connections between them, and then they become connected. But notice that there is no construction being a set of or something like that. So here in this picture, so every connection you see every connection you see is just a binary relation. Okay. Now there is a special case which is discussed very often in the theory, in network theory, and in complex systems, and that is the so-called multiplex network. The only difference to a layered graph is that in a multiplex network we have only one vertex set V instead of m different ones. So going back to my airport example, the airport would just be one vertex, and also the train station would be would be inside this vertex. So you wouldn't differentiate between the between the train station and the airport. So you don't need to draw connections in that sense in this kind of set theoretic construction. Okay, now this is to show you that you can also, of course, have combinations of a hierachical hypergraph or an M-partite graph and just normal graphs, so in this case a directed graph. And I give you the mathematical modeling example from before. So again, we want, for example, to model a disease with an SIR model. So we have here, we think it's necessary to have these 3 different classifications into age classes, locations, and disease classes. But now, for example, we want on top of that we want to draw a type graph. So what I call the type graph. Remember, a type graph is using the vertices interpreted as a classification. So here, this is a classification where all individuals of a human population which are susceptible, they would be grouped together into this capital S type. But now on top of that, you can now think about the type graph. So you would oh, sorry, a lot of disturbances in this lecture when you do the home recording. Sorry for that. So let's go back to our example. Yeah, so you want to overlay the type graph on the hierachical hypergraph. That is very often a good idea, because in this example, actually, the only meaningful type graph would be on the disease state classification, because clearly, in a disease, you have that the susceptibles are, for example, influencing. So, because they are there, they have an influence on the infectants, because they can switch to the infectant class by an infection. But of course, then the infected people also have an influence on the susceptible people by infecting them. Then, somebody who is infected in this very crude typification of a disease can then also recover from the disease. So this person would go into this class. And then you would also have the ability that as a recovered person, you lose immunity and you go back to the susceptible class or type. And that is all these arrows are now describing interactions that then, of course, would appear in a dynamic model of the disease. But for example, in a dynamic model of the disease, we wouldn't have interactions between locations. So that's why I didn't draw a type graph on that level of the classification, because it doesn't make sense that locations interact with each other, at least not immediately. You can, of course, think about that in your mathematical model. And then we also don't have a direct interaction of the H classes. This only comes in by, by having this multiple classifications. Of course, there will be then in this model, you would differentiate into H classes, and then of course, for example, the type of infectivity where you go from susceptible to infectant, of course, can depend on your H, so in which H class you are in. But it will always be the same kind of interaction from S to I. We will be more precise about that once we have defined stochastic processes, and we will see that this is exactly what's happening in an H-structured and location-structured SIR model in the classical interpretation. Now let's finish the lecture by some applications. Like we did this chemistry example where we were building up molecules from scratch, from single atoms, and then having 2 atom molecules, 3 atom molecules, and so on. You can of course do the same kind of thing in manufacturing. So the idea is that you count the number of pieces in a product, and that also gives you a very natural way of introducing a hierarchy. And it's actually also a very good exercise, because you can see quite clearly what supply chains mean. So how you need many more kinds of supply chains to make a more complex product, which is an n-piece product, like a mobile phone or a car. So you need a whole lot of underlying industry that delivers you the parts for assembling an n-piece product. So it is a very nice application, I think, of a hierarchical hypergraph, because it also shows you very clearly this set theoretic construction of being an element of. And it's also interesting because some lower level products can actually be used in several other products, and even in some that do not yet exist. So somebody has an idea, how to assemble a new product out of lower level products. This can lead to innovation. For example, somebody has a bright idea of a new use for existing things, and so you can see already from this classification very well what are some of the problems of modern industry. I should say that this kind of drawing as a hierarchical hypergraph or Bipartite graph is also relevant in computer science, because you can interpret an hierarchical hypergraph like a normal graph G as something that can be equipped with paths going through different hierarchies, and then you introduce an equivalence relationship by path isomorphy, and this then creates you a so-called a category. So I'm referring here to category theory, which establishes you a database. So it's a very fruitful. It would be another lecture, of course, but it's very fruitful to see the database connection to hierarchical hypergraphs. Let's discuss very briefly another type of classification, and that is now classification in time. Of course, you can also use, for example, in evolution, you can also use levels which are, which are then year classes. So this is, as you can see here, you have a hierarchy that is counting down million of years ago. So you go back in time if you go in this direction. And you can very nicely then draw the different levels in this hierarchy. So you can draw, for example, speciation. So this the vertices at a certain level in the hierarchy would be a certain species, and then there would be, for example, a branching here when you go to the next level. And the interpretation in this set theoretic level is that, for example, so this original species on this lowest level then contributes, is a member of the new species which has appeared here, for example. And if you have no branching, then this species, which will be which will be closer to present time, will be a little bit slightly different, will have different genetic codes compared to the species before, but it's still the same species, so there was no branching going on. So also time, that's what I'm trying to say in this example, also time can serve as a hierarchical cluster. Here is just an example which tells you that stoichiometry in chemistry, of course, naturally gives you a weight on the hierarchical hypergraph. Here I just I didn't differentiate between n atom levels. I just drew here different atoms. And yeah, here I have the original picture, and then you could also, for example, have here some things that there is no example in this case, but you can, for example, here on the 2 atom level, you could also have just one edge to the 1 atom level. So let's say, for example, if this would be oxygen, and that would be O2, then you would just have here a weight of 2 at this stoichiometry on this edge. This is just a quick outlook into how you would write down reaction schemes that are now also obeying the hierarchical order. For example, with respect to the ordering at n atom levels. This is completely new thinking, of course. You can see that you can write down such reactions. We will discuss that in future lectures in detail, so I'm just displaying this graphically here at the moment. But the idea is indeed that when you write down this explicit, you have much more information about, for example, how many atoms of a certain type are in a molecule of a certain level in this hierarchy, etc. So you can actually very naturally here define conservation laws and things like that. So we will come to that in the near future. It is clear that hierarchical hypergraphs can be used in any kind of science. But here I have one example, which is from, let's say, the social sciences, could also be used for opinion formation or epidemiology. And I wanted to show you this example because here there is, here you have two types of classifications. One, like in our SIR model type, so you have different classifications which are actually on the same level. So schools are not contained in workplaces, etc., etc. But you can have a strict linear order in this hierarchical hypergraph, for example, with respect to geography. So individuals live, for example, at certain streets. Then the streets together can be collected into certain districts, and the districts can be collected into certain cities. And so all these classification here is actually implying a linear order on the level sets as defined before in this lecture, and all these classifications here, they are just creating a partial order. I wanted to show you this kind of a transition, which is an example from demography. So, and here you can very nicely see why, for example, demography is a natural playing ground for hierarchies. So, for example, in demography, you want to describe a couple formation. So you have here, a female type, and you have here, here you have a female type, and here you have a male type, and then they are creating a group that would be a couple. So they marry, for example, and then, this would be an element. So they would become an element. So these two together form a single element, which would be a couple. In this couple group. So these would be a classification into male and female, which would be on one level of the description, and the couples would be on the next level of the description. So couples, by definition, would be groups consisting of two individuals. And so this transition here would indicate, for example, marriage, let's say, or just that the two people from now on live together, or something like that. So demography is a very good example. And then you have here couple formation. Then you can actually also go to higher order groups. So couples, for example, could form something like a tribe, or you can collect all the couples from a certain village, etc. So you could, if that would be relevant for demography, that you have the village structure and how many couples is the village separated, for example. And I think this would be a relevant information in a demography context. Then you can incorporate this in the concept of hierarchical hypergraphs. You have, of course, many problems from classical graph theory that can now be, let's say, refined in the context of hierarchical hypergraphs. So you can have hierarchical traveling salesman problems. You can have a hierarchical Dijkstra algorithm. You can define hierarchical Bayesian networks. And you can also, for example, define hierarchical neural networks. And maybe hierarchical neural networks, we will come to that at the very end of the lecture, would be a better representation of the brain, for example, when compared to normal neural networks. So I'm sure you have listened to me now for a very long time, so let's come to the end of this lecture. Let's go to the conclusions. So we have discussed a way to overcome the deficiencies of network theory, which is 1, negligence of group formations, and 2, lack of multiscale descriptions. Then we can include multi-layer or multiplex descriptions for different types of interactions or group memberships. Yeah, we have also seen that if we use hierarchical hypergraphs as transcriptions by so-called relational closure, you can also always transform them into simplicial complexes. I have not covered today the notion of hierachical simplicial complexes. This can also be done. It's a very interesting extension of algebraic topology, but I haven't touched this topic today. And then we have that M multipartite graphs are of course also graphs. So in the end we were also able to to reformulate any hierarchical hypergraph into something that is a graph. So we can also use classical graph theory in this context. And we have discussed briefly or touched the topic that we can then use the hierarchical description of a problem also to introduce dynamical models. And this will of course be relevant for part 2 of this lecture. So more or less this now concludes part 1 of the lecture, which was about relational and structural models. And yeah, very soon now we will go to stochastic processes. But for now I would like to thank you for listening to me for such a long time. And yeah, I wish you all the best.